Thank you, Charlie. So as Charlie said, my name is Badri Hiriyur, the director of AI, Core AI specifically, and we've been working on several projects that leverage the power of machine learning and AI, specifically targeting our AEC industry. And I'm excited to present to you one of the flagship projects that we've been working on. We're calling it T2D2. Stands for Thornton-Tomasetti Damage Detector. So, as I said, it leverages the power of AI, specifically narrow form of artificial intelligence, computer vision, to automatically detect defects, deterioration in various kinds of structures. And it has been deployed on mobile platforms. It has drone interfaces, and it also works with traditional image and camera feeds from handheld cameras. And it uses the power of deep learning. So instead of manually feature engineering all of the required features that denote what we are looking for, it uses deep learning, which can automatically extract all of the required features to identify various types of defects, be it in concrete structures, masonry structures, stone, stucco, and so on. It's been trained on thousands of images that we have collected in our TT database over years of inspection of various kinds of structures. As I said, it has been deployed on a mobile platform. This was one of the first proofs of concept that we had. You walk around with this handheld camera on a mobile phone, and it's going to automatically detect all of the different types of damage that you see in various types of structures. Some pavement cracks and spalls being shown here, and it can tag the location and the time at which it was recorded, and as you walk around an entire structure, it's going to keep a record of all of the damage around the structure. So this is going to significantly enhance the productivity of an inspection process. I mean, what would take probably a day can be completed in a matter of minutes or hours. We have also worked over the last year on several improvements to the pipeline that enhance the detection. Initially, we got some false positives, some false negatives, and we've been working tirelessly to reduce these false positives and false negatives. So we've constructed an enhanced detection pipeline that have various subcomponents that are all powered by machine learning. So we've got a structural versus non-structural classifier, proximity classifier, material classifier, and so on, all of which work towards improving the accuracy of detections. And as I said, it's going to work with handheld cameras, drones, and mobile interfaces as well. Towards the end, you combine the detections from all of the sub-images. We've done subgridding and take it to the next step, which is automatic damage report generation. And here, this is a quick demo about the efficiency that's brought about in the inspection process by using our software. Where, we have hundreds of images here with all kinds of damage, but if you had to manually go through each of them, trying to pick out what is the damage, it would take hours. And you could miss a lot of defects as well. But here, in a matter of seconds, we're able to detect all kinds of damage in hundreds of images, and within a matter of seconds, it's also going to generate a report, an HTML report, that summarizes all of the defects, that summarizes all of the detections that it has found. And it's almost ready to be presented to the client, and you can review it, make sure it's correct, make any modifications, and then submit. So what would take hours now takes minutes. Now you can scroll through the list of detections. You can zoom in, find what was detected, and see what the confidence was, and so on. And we have also worked on improving the interfaces so that all of this can be done on the cloud. What we're showing here was a manual command line interface, but we are deploying it on the cloud so that all of this can be done by any one of our engineers using a browser. What makes our product even better is that it is not fixed in time, so it's continuously learning. Right now, it's been trained on thousands of images, but eventually it will continue to be trained on hundreds of thousands of images, and this will improve the performance of the detection. So you get the camera feed from any of those sources, goes to our inference server, which is deployed on the cloud. It returns the detections, which is presented in a mobile or web interface, and our engineers, our trained engineers, are going to review that, make sure it's correct, and if there are any corrections, make those corrections and submit it back to our database, so all of our models get retrained, and the accuracy of the models increase over time. We have deployed it on several projects. I'm just going to show a couple of them here. So this was the drone inspection of a building in Long Island. And this was I'm just showing a portion of the video here, but this was a video that ran for about 15 or 20 minutes. And as you can see here, this was done using our enhanced detection pipeline. So the large images, the high-resolution images, were actually broken down into sub-images so that you're virtually zooming in on the damage, and you're able to capture all of this almost in real time. And also, we've used all of these camera frames to build a 3D photogrammetric model, overlay the damage detection that was found in each of those frames onto the 3D model, and present to our clients a 3D model with all of the detections being overlaid. You can click on any of those dots, the red dots being spalls, or the blue dots being cracks, and there's vegetation growth also being detected here. And so this presents almost like a digital twin of the state or the health of the facade and building envelope of this building. We've also used this on drone inspection of an apartment building in Florida. This was a stucco facade, and this actually is significantly hard even for humans to detect some of the defects on the structure, but we were able to enhance the detections by applying color corrections and various corrections to the images, pre-processing it before passing it to our pipeline, and we were able to detect minute damage that would have been missed even by a human inspector. You can imagine that there's significant potential for this. You have hundreds of thousands of buildings, tall facades, and if you have to swing down like the window washer unit, or if you go up on a scaffold, this would take hours, days for a project like this. But with drones combined with automatic damage detection, all of this can be done very efficiently. We've also worked on several other projects. We've provided a damage inspection report to a client in Toronto in a matter of minutes, where it would have taken hours or days. The potential for this technology is, of course, endless. We've shown some examples for building facades, but this can be easily extended to bridges, tunnels, even oil and gas facilities, nuclear and defense applications as well. And we've been talking to several people. There are lots of interest in this technology, and we're very excited about the prospects of this going forward. Thank you, and I'm going to hand it over to Sergey and Emil for their updates.
Well, hi guys. Good to see you all. My name is Sergey Pigach.
My name is Emil Poulsen.
And we are here to tell you about Swarm. So the modern-day AEC industry operates within an ever-increasing number of constraints. Most large-scale projects spend a great deal of effort tackling issues of energy efficiency, environmental sustainability, structural optimization, accessibility, the list goes on. Combine that with the undying human need to have your cathedral just that much taller and that much curvier than the neighbors, and you kind of land on the early 21st century architectural sensibility that looks something like that. Now, in order to produce projects of this nature, one needs very sophisticated tools. And the problem right now is that most of those tools look something like this. And don't get us wrong, we passionately love Grasshopper. But the issue is that when you start tasking the designer with increasingly sophisticated computational questions, you really start to divert their attention from the issues that they should be focusing on, which are the questions of design. Which is why in most large firms, at some point there was a point of kind of organic separation between the designer, who is the person who spends sleepless nights trying to deliver the project that fits all of those constraints, and the computational specialist who facilitates the designer and builds tools and workflows that make all of this, in fact, possible. And usually it kind of goes down like this. You have the computational specialist who spends hundreds of hours building a set of tools and workflows. But that's only half the battle, because once the tool is built, your next challenge is distribution. And you have to make sure that every member of your design team is willing and able to use the tool that you've built for them. And as some of you may know, that's not always easy. Turns out that a lot of designers are not very comfortable with the Grasshopper environment, which is not their fault, because it's really not their domain expertise. But for us, it was really the goal to try to make sure that designers can stay designers and computational specialists can stay computational specialists. So this way, everybody kind of exists in their own line of work where they do what they do best. Because otherwise, when the deadlines kick in the designer realizes that they have no time to sleep, let alone to learn this new tool you just built for them, they will come to you and they will ask you, hey, can you do this with me? And at that point, you're pulling all-nighters alongside the design team, and that's less than ideal. And the saddest part is that, at the end of the project, that Grasshopper definition that you spent hundreds of hours building usually gets stashed away somewhere in the depths of the network drive, never to be seen again.
Okay, so this is a pattern we've seen quite a lot of times across our company. And I'm going to give you a quick little snapshot of how Core Studio has been trying to solve this throughout the years. So in 2012, Core Studio worked on a project called Remote Solving. It connected design models and analysis models through the cloud, which allowed sort of our project partners to use our bespoke engineering tools remotely. And then we had 2015. We worked on a project called Platypus, which is a tool that allows Grasshopper authors to stream geometry to the web in real time. It sort of allowed you to share 3D model views of your stuff while still sort of tweaking it. And cool, all right. We presented Asterisk last year, which is sort of a structural optioneering tool. And people really digged Asterisk. It was really awesome. But as it sort of started to get used in real projects, so people started to ask for more features. And as Asterisk was a bit of a beast from a technical point of view, iterations took really long time to sort of implement new features. And then last year at the hackathon, we, together with some really awesome folks, made a REST Hopper, which is a system for remote solving Grasshopper definitions. So after the hackathon, we started to sort of bring back the conversation about remote solving again. Sort of what would be sort of the next step? We talked about our internal needs, and we knew that this new tech could have some real value to TT. But we also started to discuss sort of the potential opportunities outside of TT and also outside of the AEC industry. So here we are, 2019, presenting our next push, basically our next attempt in this journey. So Swarm is a marketplace and a system for sort of remote solving Grasshopper definitions. The concept really here is to connect designers who need tools with super users that are building them. So from a technical point of view, Swarm encapsulates Grasshopper definitions into clean, shareable, cross-platform apps. So an integral part of Swarm is the marketplace. This is where you find and share apps. And the apps can be either private, shared with specific users, or shared within organizations. They can also be public, which means that they're available for pretty much anyone to install and run, either for free or with a price tag, depending on the preferences of the author. So the first step you want to do to run an app is to install it. Once that's done, the app can now be shown in one of our Swarm plugins, and here is the Rhino client that we're showing. So each app is presented as a condensed and simple user interface. So as a user, you configure your inputs, you hit run, and you get the results back. So obviously the designer doesn't really have to know anything about Grasshopper to be able to run a Swarm app. An important detail to mention in this context is that the underlying Grasshopper definition isn't really solved on your local station. All the inputs and instructions are sort of bundled up into a package and sent over to our servers that sort of solves the Grasshopper definition and returns the outputs. So this means that Swarm doesn't have to be run from a Rhino document nor a desktop. Here's a little prototype of running the Swarm app from our web client. Our focus has been sort of on the desktop clients really, because that's really the sort of natural place where our TT engineers do most of their work. But we think this turned out pretty snappy. So we're also playing with a couple of other plugins. Here's the Revit implementation on the left. And we also made a prototype for Illustrator, which we're pretty excited about. So as I mentioned, we really hope that Swarm can sort of help computational design to be leveraged in other communities and practices and industries. And they might be using completely different tools than what we use. So since we have a lot of computational specialists here in the crowd, we wanted to give you a little quick demo of what creating a Swarm app looks like. So you open up the Grasshopper definition that you want to create the app from. The next step is to indicate to Swarm what the inputs and outputs are, which you do using our Swarm Grasshopper plugin. You give the inputs and outputs a name, and then lastly you hit the upload button, which will send your Swarm app to the Swarm mothership. Cool, so once it's uploaded, you can now find it in your account. Here you can start sort of editing the app. You can add descriptions, pictures, sort of creating a nice little package out of it. Only the author will be able to see it at this point. But as I mentioned, you can share it with, either with specific users or within your organization, or even make it public. You can also allow users to download the source definition if you want. So we've also made a little bit of an effort to make it as hackable as possible. And if you wonder if we have an API, my good friend Sergey has some good news for you.
Because, yes, we do. And the wonderful thing about developing on top of the Swarm backend is that because you're building out the business logic of your application in Grasshopper, the time that it takes to you to prototype, test, and deploy is cut down dramatically. And we've been experimenting with this in the office. So here you can see two examples of core applications running on top of the Swarm backend. So on the left, we have the column design app that runs inside of Revit. And it's a tool that helps our engineers to calculate trib areas in Revit for column design. It also offers a series of repair operations that kind of help you prepare your model for a column design process. Now, each of the buttons and methods in that application, in the most extreme cases, took us no more than 20 minutes to design and deploy, as opposed to spending hours, days, or sometimes weeks implementing the same functionality in .NET. And one of the coolest part was actually that some of those methods were provided to us by TT engineers who don't know how to code, but know Grasshopper, so they were able to directly contribute to the project, which we thought was pretty awesome. Now, on the right is another example. That's Construe framing repair, also running on top of Swarm API. Now, that's not deployed yet. We're testing it in-house. It's in active development at the moment. But here again, we see the speed of development increasing by orders of magnitude. And Emil mentioned before that one of the challenges we've experienced with Asterisk is that once we committed to a certain way of using our app, it becomes increasingly more difficult to accommodate all the other numerous ways other people want to use it. And the beautiful thing about being able to develop fast and having both the backend infrastructure and the front end kind of figured out for you is that now you can afford being flexible and having a lot of options. So here you can see actually the family of asterisk swarm apps that each cater to a slightly different user experience and responds to slightly different demands. And it took us several months to develop the front end for the web app. This family of swarm apps appeared in like less than a week. And development speed is not the only advantage of using Swarm API, because the cloud compute technology also offers you ubiquity, meaning that now it's extremely easy to port your app to other platforms. So here you see another iteration of the Asterisk app that's been tailored for running inside of Revit. So instead of interfacing with simple geometry, you're actually able to consume and bake out BIM elements. And going to other platforms is something that we're certainly very excited about. So we have the Swarm client in Rhino and Grasshopper, and we're also have prototypes for Revit and Illustrator. But we want to look at other platforms in other fields, which means that now we have the ability to bring powerful parametric tools to industries that traditionally existed outside of the Rhino ecosystem and haven't really been exposed to those types of workflows. And I just want to, in conclusion, go back to the idea of the marketplace, because I think it really captures our vision for Swarm as this open platform where designers and computation specialists and creators can all freely share multiple, designers from multiple disciplines can all freely share knowledge and apps and tools and workflows. It provides the way to kind of put your work out there as free open sourced apps, or be compensated for it if you choose to do so, which we hope will facilitate more in-depth and involved development. But all that we can offer is the original vision and the tech. So we really want the community to tell us where you want this project to go. So please reach out to us. Tell us, would you like to use Swarm? How would you like to use it? Where do you want to see it? What client do we want to, do you want us to build next? So yeah, please come talk to us. And thank you very much.